Continue. Here we go. Today is the 25th. Lecture number 12. 13. We had 12 last time. Kershaw, yeah, hopefully everyone passes through this class and makes it to the next round, whatever that next level is for any of you. Hope to see everyone go through. So last time we've spoken about several new things, right? We've talked about orthogonality, what makes two vectors orthogonal using the dot product. So we heavily emphasize dot products, and dot products. We define dot products as using the cosine version, but there's also the other version that deals with the components of the vectors being multiplied by components and then adding them all together at the end. So that's another way that we define dot products. And dot products is an essential operation in linear algebra, particularly with vectors. And we utilized that. We ended up last time using dot product to help us find the projection of a vector along another vector. So we'll see more of that today. And in particular, I wanted to go back to that definition of dot product that we have. So we're gonna just recall the cosine version, I would say, right? This is just a cosine version of dot product. So if we have two vectors, so if V and W are vectors in Rn, then V dot W is equal to the norm of V multiplied by the norm of W multiplied by cosine of the angle theta, where theta is the angle between the two vectors. And then from this definition, we are able, using some algebra, we're able to define cosine in terms of the dot product and the norm of vectors. So think of it this way. We're defining cosine as a product of the dot product of two vectors divided by the norm of two vectors. We can also do this now. And in particular, we can define exactly what cosine is, what the angle is, by using the inverse cosine function of the argument being the dot product of the two vectors V and W divided by the norm. So we can find the angle. The idea is we can find the angle between any two vectors as long as I have the two vectors. As long as you give me the two vectors. So let's find it. So find the angle. Find the angle theta between the vectors. And I'm going to give you one vector called V 1, -2, and a W being -4, 3. So before we use the formula, I just want to draw this out, give a little sketch, just so that I can visualize this and have a better understanding of what's going on. So we get 1 comma negative 2. So 1, negative 2. This is my first vector here. We'll call this V. And my other vector, negative 4, 3. Now, I think the interesting question would be, first of all, what angle are we speaking of? As you can tell, there are two angles in the sense that are between the two vectors, right? Between W and V. You can consider this being one of them, this being the angle between them, or you can think about this angle being between them. So which one is it that we're going to find? The acute angle, well, actually, this angle isn't acute because acute means to be less than 90. But just by visually looking at this, this angle exceeds the 90 degrees, right? So it's not necessarily acute. What you have to recall is cosine. And in particular, not just cosine, but actually recall cosine inverse. So if you remember inverse trig, this is from pre-calc. I don't know if you guys remember this, but inverse functions come from one-to-one functions. Those are the functions who passes the horizontal line test. And if you remember, cosine is not naturally one-to-one, right? Cosine has a wave-like structure between 1 and negative 1, and it keeps going up and down, up and down, up and down, right? Like a wave. The problem is, to find the inverse of said function, right? It wouldn't exist in this way. Why not? Because the horizontal line test is failed immediately when you draw one horizontal line. It crosses the graph more than once, an infinite number of times, which indicates that this function is not one-to-one, meaning that there is no the y values that I have represented by this horizontal line has more than one x value associated with it. That's what it means to be one-to-one. It means that for every y value, there's only one x value. The same way that in a function, every x value is mapped or assigned to only one y value, the one-to-one functions not only have every x value being mapped to one y value, but every y value has only one x value. So Mir says, so we say negative pi over 2 to pi over 2. Not exactly. What we do is we restrict the domain between 0 and pi. Do you remember this? And then we take only this strip of the cosine curve. So we restrict the domain. So my domain of cosine of my restricted domain is from 0 to pi. And then my range stays intact. My range is from negative 1 to 1. So when I apply the inverse, when I find the inverse, remember what inverses are? This is x and y. My inverse function, what happens with my inverse function? The x's and y's are swapped, right? That's usually the way inverses are defined. So my x's become y's and my y's become x's. So in a sense, I'm taking this graph here and I'm rotating it while reflecting it in such a way that my x-axis becomes my new y-axis. So this becomes from 0 to pi. So vertically, this becomes 0 to pi. And then my y-axis becomes my new x-axis. So I go from -1 to 1. So then my function looks something like the following. It looks something like this. If I draw this correctly. It looks like I'm drawing my cosine curve. Instead of drawing it this way, I'm drawing it like this. That's what it would look like. So then what's my domain? What's this? Again, this is cosine inverse. This is just cosine. And this is important. This is just like side commentary, but this is important. So my domain is what? -1 to 1. And my range is what? 0 to pi. Why am I saying all of this? What I'm saying is that the angle that's produced from this cosine inverse function will be, the angle will be between 0 and pi. That's what the output of this function gives me, between 0 and pi. And what is pi? Radiant. It's 180 degrees. So the angle that I'm going to get out of the applying this formula will be the angle that's smaller than 180 degrees. So this is the angle that I'm given. I'm going to be given this angle theta. That's what I'm going to be looking for. So when I say the angle between the two vectors, I am finding the angle smaller than 180, not the bigger angle, even though this angle is also between them. But the angle between that we're looking for is less than 180 degrees. Okay, so we're expecting to find that angle. So now we have that understood. I'm gonna find the angle. So angle is what? Cosine inverse of u dot, pardon me, I'm using v. V dot w divided by the length of v times the length of w. So I'm gonna do this step by step. The first thing I want to do is v dot w. V dot w is gonna be what? So v is 1. Remember, this is like saying v1 times w1 plus v2 times w2. This equals 1 times -4 plus -2 times 3. -4 minus 6, so this equals -10. So the dot product between v of v and w is -10. Then I'm going to take the norm of v and take the norm of w. Find the norm, find the length. And in two-dimensional space, all we're doing is taking each component and squaring it. So v is 1 squared plus, this is -2 squared. So I get rad 5 as the norm of v. And then of w, I got -4 squared plus 3 squared. But this is like saying 16 plus 9, which is 25. Rad 25 is 5. So theta will be what? Cosine inverse of -10 divided by 5 rad 5. And you can simplify this. You don't have to, but I like simplifying things. This becomes 2, right? 2 rad 5, 2 over rad 5. So this is my theta. Okay. So this is my theta. And this is the actual angle. So you can leave, this is exact value. This is the exact value. Now, what you can do as well is put this in your calculator. Let me show you how to do that. Your calculator. So we are going to, for those of you who have the TI-84, I'm gonna put, so one thing you have to keep in mind about using inverse trig is the mode you're in. So for now, I'm just gonna leave it in degrees because degrees makes a bit more sense for our understanding than radians does, especially what the radians that the calculator produces. So I'm gonna use second cosine, that's cosine inverse. I'm gonna use the function to make a fraction, divide -2 divided by the square root of 5. Whoops, that's not what I want. Delete. And then I'm press enter, and the degree version is 153.43 ... degrees. So that's roughly what my angle is. It's roughly 153 degrees. I'm gonna try one more time, but this time I just wanna find what the radians would be. So I'm gonna go to mode and change it to radians. And just to keep in mind that it's gonna be a much different answer. It's gonna be 2.6. But again, what's the units? 2.677, this is radians. So 2.67 radians approximately measures up to 153 degrees. So the angle in between these two vectors that I'm given is exactly what we found. It's cosine inverse of -2 over rad 5, which if in its degree form is 153 degrees, and in its radian form, it's 2.6 radians. Okay, is that clear? Any questions about applying this formula? How to find it using the calculator? Is that clear? Any questions? No questions. So again, I'm just applying the formula that I showed you about dot product, rearranging it so I can find the angle between the two, any two vectors, by utilizing the dot product and utilizing the norm of each vector. Okay, is that clear? Yes, sir. Okay, good. And now, so this is with vectors in R2 space, right? This is in our normal Cartesian plane. And then if I'm in a three-dimensional space, it's the same idea. It's just that now I have a third component, but the steps are identical. The dot product, I will just have one more term being multiplied, right? And added. And the norm, I'm gonna have one more component squared. But then the next steps here are identical. So I'm pretty sure you're gonna have that for homework, and you can have more practice with that in your homework. Okay. Okay, so now we've talked about the angle a bit, and now we left off last time with projections, orthogonal projections. And I showed you a derivation of the formula for the orthogonal projection. So the idea is that I have a vector and I have another vector. And so this is going to be vector v. This will be a. This is why, of course, I'm using an example in the xy plane because that's something we're comfortable with, but then you can extend this formula to any dimensional, n-dimensional space. So the idea is that I should be able to find the vector along the vector A that is a projection of V where the projection splits up the vector into two components, one being orthogonal to the projection. So this vector here, this one here is the orthogonal projection. So we call this the projection of V onto A. This is the vector that is the orthogonal projection of V onto the vector A. And I'm just gonna call this W. And so then I'm gonna call this vector here, it's another good letter. I'm gonna call this Z. So the idea here is that W, if I take W and I add it to Z, I get V. So that's the idea. So the idea is that W plus Z is V. And the idea is that W is perpendicular to Z. In other words, W times Z, or dot product Z, is 0. Remember, when two vectors have a dot product equal to 0, they are orthogonal. So W and Z are orthogonal. Just gonna write this over here as a separate point. W and Z are orthogonal. In other words, perpendicular. And they make up the sum. The sum makes up the original vector V. So that's the idea behind orthogonal projections. And there's a formula for this, of course. So if you take the projection of the vector V onto A is given by the formula that we derived in the previous lecture, which is the dot product of V multiplied by A divided by the norm of A squared multiplied by the vector A. Again, we derived this last time. Very important. And remember that we also found another way to rewrite the norm of A. Remember the norm of A? So recall that the norm of A, or any vector, call it V. The norm of V is equal to the square root of V dot V, or the norm of V squared is equal to V dot V. In this case, I have the norm of A squared. So the norm of A squared is just going to be A dot A. So I can write it in this fashion, or I can write this as the projection of V dot A divided by A dot A multiplied by A. There's a lot of A's here. I just want you to keep in mind that this fraction here is a scalar. It's not a vector. Why isn't this a vector? It's because this is the dot product, which gives you a real number. And this is the norm squared, which is also a dot product, which gives you a number. So this is a number divided by a number. So this is a scalar. And we're taking the scalar to multiply it to the vector A so that I can either minimize or maximize this vector so that it fits right underneath this vector V so as to produce two vectors whose sum makes up the vector V and whose scalar multiple of the vector A becomes what's known as the orthogonal projection of V onto the vector A. Is this a formula the same if we have to project onto a line and origin? I'm not sure about the origin part, but it is to project it onto a line. That's exactly what's happening. You can think of this as a whole line. You can think of this as being a whole line, and you're trying to project something upon this line. This would be the formula, but this formula is particularly used for vectors. Oh, there's a problem like that. Okay. Yeah, the origin part, I'm not too sure about the origin. I think I've seen some of them. Yeah, so I think what you're talking about, the onto a line in origin, it literally just means the vector going through the origin. Because if you consider other lines, it becomes a bit more complex to do that because it doesn't go through the origin. When something goes through the origin, like these lines, it's a little simpler to utilize this formula and apply the projection. So yeah, the assumption is that the vector that we're dealing with, right? We kind of make the tail of this vector, we make it the origin, and then it kind of just works out that way very nicely, utilizing this projection formula. Okay, so let's see this. Let's see this in action here. So let me have an example. So I'm gonna have another vector here. I'm gonna call this vector here. Again, 1, -2. I'm gonna have the vector A being -4, -3. And let's see, yeah. So I'm gonna draw this out just to give us an idea of what's going on. I got 1 and -2. So I got 1 and -2. So I have this vector here, called this V, and then I'm going to have -4, -3. So 1, 2, 3, 4, and -3. So this is my A value. And I'm taking V and I'm projecting it downward along this line or this vector, whose, if you multiply by scalars, right, gives you a line through the origin. I want to find what is the vector V projected onto A. What is that going to look like? Again, this is not going to be like the biggest orthogonal projection, but do you see how if you consider this as like your ground, your level playing field, a level field, and this becomes like your new level, and you're projecting this straight down to create a right triangle. This here will be the projection of this vector along this vector A. So I want to find what is the projection. I want to find the projection of my vector v along A. And you can also do it the other way around. You can also say, hey, what happens if I take this vector A and project it along this vector v? What would that look like? What would be the vector? So you can also do that as well. So let's see what this equals. Using the formula, we get v dot A over A dot A times the vector A. So what is v dot A? It's going to be 1 multiplied by -4 plus -2 multiplied by -3. I get -4 plus 6, which equals 2. And then I'm going to get A dot A, which is -4 squared plus -3 squared, which equals 16 plus 9, which is 25. So then the projection of V along A is going to equal 2 over 25 multiplied by A, which is -4, -3. Again, you can treat the vector as a column vector or as a comma delimited form, which is -4 comma -3, which is like the n-tuple version. But I'm just going to leave it as a comma, as a column vector. So I'm done. This is my vector. This would be the vector. Let me color the green color. And of course, you can rewrite this as something like a single column here. This would be -8 over 25, and this would be -6 over 25. You can also write it this way. That's also acceptable. And this would be something like this. This would be the projection. The projection of V along A. Does that make sense? Can anybody see that? So this here would be the projection of this vector V along A. Any questions about what we're looking for, what we're finding, and how we apply the formula to find it? No questions? Okay. Well, I hope that's clear. So let me do a three-dimensional version of this. So what if my vector V three, 1, 3, 1, -7, and A being 1, 0, 5. So again, I want to find the projection of the vector V along A. We'll use the formula V dot A divided by A dot A multiplied by A. So this becomes very formulaic. This is V dot A is equal to 3 times 1 plus 1 times 0 plus -7 times 5. This becomes 3 minus 35, which equals -32. What is A dot A? That's equals 1 squared plus 0 squared plus 5 squared, which equals 26. So this will equal negative 32 over 26 times the vector 105. And if you reduce the fraction, you get negative 16 over 13, 105, which is the same thing as saying negative 16 13ths times 0 times negative 80 over 13. So this is the vector of V being projected onto the vector A. And I will spare you my attempt to draw this, sketch this in a three-dimensional plane space. This is not as simple, but it's the same idea as two-dimensional space and dealing with vectors that for which you're trying to project upon another vector. It's the same idea. Okay. So any questions thus far? Is this clear, guys? Is this particular task simple enough and understandable for what we're trying to find and how we find it? So far straightforward. Okay, good. Good. So we have the formula for projection, and particularly we're talking about orthogonal projection because we're creating two angles that are two vectors that are orthogonal to one another. Okay, so a few more things that I want you to be able to do is so if I'm given example, so if I'm given a vector, let's go back to the two-dimensional plane, 6, 2, and the vector 3, negative 9. So rewrite V as a sum of orthogonal vectors. So I'm going to use one of those vectors will be the projection of V onto A. And I'm gonna call this I'm gonna call this the vector W. And the second one is to find the vector Z, which in this case will be orthogonal to Z and whose sum gives me V. Okay? And then we'll do one more thing after this related to this question. But again, the two-dimensional space is a bit easier to deal with because we've seen it. We've seen it a lot and it's easy to draw. So this will be 1, 2, 3, 4, 5, 6. 1, 2. So this here is my vector V. And then my vector A is 1, 2, 3, but negative 9. So it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9. And so I got something like this. This is A. And again, I want to do what? I want to draw or I want to find the vector that if I were to put a light source right above it so that it's perpendicular to the vector V, the vector A, pardon me. If I draw this here is now representing the orthogonal projection of V onto A. And in doing so, I'm able to draw two vectors that are orthogonal to one another, but whose sum is V. So the first thing is find the projection of the vector V along A. So again, the formula now becomes eventually second nature. So V dot A, when we do V dot A, what do we get? We get 6 times 3 plus 2 times negative 18. And so what does that become? This is 18 minus 36, which equals negative 18. And then what does A dot A become? 3 squared plus negative 9 squared, which is 9 plus 81, which is 90. So I get negative 18 over 90 multiplied by A, which is 3 negative 9. You can divide both things by, both numbers by 9, and you get 2 over 10, which is a fifth. You can actually divide it by divided by 18. Okay, divided by 18. This becomes 3 negative 9. So this becomes 1/5, right? 18 over 90. Divided by 2, yeah. Let me see something, 18. So this then becomes negative 3/5, and this becomes positive 9/5. So this is my vector. That's the projection of V, the orthogonal projection of V along the vector A. So I found it, and we labeled this vector, we call this W. Now, how do we find the second component? So we found the orthogonal component along A. Now, how do I find the orthogonal component perpendicular to A? So if this is W, if this is W, then I want to find Z. How would you find Z? I know V, I know W. The projection of V along A is W. Now, how would I find this vector Z? Anybody have any ideas? No? Nobody? No one? No one have an idea of what to do? Pythagorean theorem. Now, so we kind of went away from the Pythagorean theorem because the Pythagorean theorem deals with right triangles. And indeed, this creates a right triangle, but we're dealing with vectors that are the sides of a right triangle. So we have to deal more with vectors instead of the lengths of the sides. Again, norm is finding the length of a vector. I can't find what the length of the vector is if I don't have the actual vector. I want to find what is the vector If I found the projection of V along A, which is W, I found it. I know what it is. This is what it is. They give it to me. So let me just say 1, this is 3, -9. Just want to make sure I computed this correctly. Well, actually, this is incorrect, guys. You guys see why? Yeah, that's right. Thank you, Amaya. There's a problem right here. I got 18 out of nowhere. This is for being a bit too hasty here. This is -9. I actually get 18. So I get 0. So what does that give me? In the you have the idea now. That's the idea. You subtract. So we actually are to subtract. So what's the idea here? V dot A is 0 actually. So this is actually 0 on top. So what is this telling me? What is this telling me? The projection is 0 because anything divided by 0 is the vector 0, 0. So what happens if my projection is 0, 0? So the projection is actually 0. So what does this mean? We actually can't decompose this along like this. Because why? We show by the dot product that V dot A is 0, which implies what? What does this imply? V dot A equals 0 means V is perpendicular to A. Already. It's already perpendicular. So if you already have two perpendicular vectors, if you project an orthogonal vector to another vector that's to the vector that's orthogonal to it, then when you project it downward, it goes straight to the origin. So actually, there is no projection for this. This is a bit of a trick question here. There is no projection. They're already orthogonal. V and W. So the projection of V along A is already the vector 0 because V and A are already orthogonal. As we saw with the dot product. So the dot product gave me 0, so the two vectors are 0. So let me reattempt this question that I want to give you guys. But these numbers here just worked out this way. It worked out this way. So again, that can happen, guys. We can have a problem where the two vectors are already orthogonal. So if you're already orthogonal, there is no real reason to project them because on one vector to the other because they're already orthogonal. So I'll give you another one. I'll give you -1, -2, and -2, -3, -2, 3. So I think this one will have a different outcome. So again, let me draw this out. So here we have -1, -2, 1, 2. So this is -2, and you're given this vector here, which is V. And then I want to look at -2, 3. So -2, yeah, 1, 2, 3. So I got something vector like this. Some vector like this. And we'll see what happens here. So this is A, right? And I want to find, let me make this a little smaller, X and Y. I want to find the projection of my vector V along A. Formula V dot A divided by A dot A multiplied by the vector A. So what does V dot A equal? It equals -1, -2, plus -2 times 3. This equals +2, and this equals -6, which equals -4. What is A dot A? Is -2 squared plus 3 squared, which equals 4 plus 9, which is 13. So this equals -4 over 13 multiplied by A, which is -2, 3. So then this equals +8 over 13, and this equals -12 over 13. This is the projection. Now this is an interesting case. Why is this a bit interesting? Is because normally our vectors, you can think of one vector being directly above or over the other vector, right? Normally we have vectors like we had in our original example where the vector, one of the vectors is directly over it. And so this here becomes the projection of this vector along this vector. But if you look at this example here, it looks like we're projecting, this is -2, 3, right? We're projecting V along A. If you'd see this vector V is not necessarily over A. It's a little bit like on the outer part of A. So if A is going this way from the origin to this direction here, V is a bit on the other spectrum of it's going in the opposite direction. In other words, yeah, the projection itself of V onto A is on the opposite projection, on the opposite direction of the original vector A. So that's still okay. Think about A being extended on the other direction, and the projection is this one here. This also is completely possible. And this here is my projection. This is my projection. This is my projection of V along A. So this can happen where the vector that you have and the vector that you're trying to project is being projected onto a vector that's going in the opposite direction that your vector is going in. And in that case, your projection will be the same. It's on the same vector. It's on the same vector who's being extended, right, through this line here, through the origin. It's just that it's on the other side of the direction. And it coincides with what we got as our final solution here. We have a positive x value, so it's on this side, but it has a negative y value, so it's in the fourth quadrant. So that's going to be my projection. And now the question becomes, once I found the projection vector of V along A, I want to find the vector that when you add it to this vector here, I have an orthogonal set of vectors whose sum gives me V. I know the projection and I know my vector V. So how do I find this vector here, Z? And I think Inderpreet answered that question. So if I know W, W is known, and I know V, W is known, V is known, and I know that W plus Z equals V, then Z is equal to V minus W. So it's really just a subtraction problem now. So this missing vector that I'm looking for is V, which is what? V is -1, -2. So -1, -2 minus the vector, projection vector, 8, 13, -12, 13. So when we subtract that, we get -1 minus 8 over 13. This becomes -2 plus 12 over 13. Same denominator. I get negative 13 over 13 minus 8 over 13, and I get negative 26 over 13 plus 12 over 13. And I get negative 21 over 13, and I get negative 14 over 13. Does that make sense, everyone? So not only are we finding the projection of V onto A, we're also finding the other component that whose sum with the projection gives you the original vector V. Now, how can we be so certain that everything works out? Well, you can check. You can do several checks. You can check by showing one thing, that when you add W plus Z, you indeed get V. So if I were to add W back, and it's supposed to work out, right? Because that's how I found it. I use the same formula. So W is -1, -2. And if I add this to negative 21 over 13 minus 14 over 13, the question is, would I get -1? Whoops, wait, W. This is W, pardon me. This is W. So this is 8. This is 8, positive 8. Positive 8 over 13. And then I got -12 over 13. So when I add this, I should get -1 over -2. And if I add the numbers, I do get indeed that that sum. And now the second thing that can help you is to see whether or not the dot product itself, whether or not that's equal to 0. That's really the question that you should ask and be able to determine using the dot product, whether or not the dot product equals 0. Because if it does equal 0, then it indicates that I found the two vectors that are orthogonal to one another. So W here is 8 over 13. I'm multiplying that with -21 over 13. And then I'm adding that to -12 over 13 multiplied by -14 over 13. Does this equal 0? So really, it just boils down to, do the numerators, do they multiply the two numbers that give me a sum of 0? So if I put in -21, I get 168. I get -168 over 13. And then 12 times 14 is also 168 as well, as expected. So this is 168 over 13, and it does equal 0. So indeed, I found two vectors. One of the vectors here would be this vector here. This would be Z, which is what I found here. And I found W, which is the projection of V along A. So these two vectors, when you add them up, give you the vector V, and whose dot product is 0, indicating that these two vectors are orthogonal. So far, so good. Any questions about projection vectors, orthogonal projection of vectors? Any questions about finding the vectors and applying the formula? Anything at all? No? Clear? Excellent. Excellent. Okay. And so now, what would be the norm of the projection vector of V along A? What would be the norm? So again, recall that the projection of the vector v along A is v dot A over A dot A multiplied by A. And what I want to find now is the norm of the projection vector. I want to find the norm of this new vector. I want to find how big is it? How long is this new vector? But remember what I said. This little fraction here is a scalar. It's not a vector, it's a scalar, it's a number. So this is a number that when you take it out of the square root, right? Because remember, this norm here is a square root, and this is taking the components of A and squaring them. And each of these components of A here is being multiplied by the scalar. So we're squaring this. But when you take something squared, you can factor it out. And when you factor something squared out of a square root, you get what? You get the absolute value of v dot A over A dot A. You get the absolute value. And you're multiplying that with the norm of A. But recall, what is the norm of A? There's a lot of recalling here. What is the norm of A? Remember this, the norm of A is equal to the dot product of A, the square root of the dot product of A. Or in other words, the norm of A squared is A dot A. So I can rewrite the following. I can rewrite this as the absolute value of V dot A all over the norm of A squared. Does everybody see that? I can rewrite this as the norm of A squared. This is a number squared, and this is a number, a whole number, a real number. And what happens? This here cancels. So the projection of V along A, if I want to find the norm of that, I can also rewrite this as the dot product of V and A over the norm of A, or in other words, V dot A, absolute value, divided by the square root of A dot A. So this has become very formulaic in its presentation, but really it just stems all from the same tree, same vein, which is this projection here, this formula. All right, guys. So any questions about this? Any questions? Okay. Oh, and actually one more thing. If you guys recall, what is a lot of recalling today? What is V dot A? So recall here that V dot A is the norm of V multiplied by the norm of A multiplied by cosine of the angle, right? Isn't that what the formula is for dot product? So actually, there's one more way of writing the projection of the norm of the projection of V along A. I can replace this inner dot product. I can replace this as the norm, the absolute value of the norm of V times the norm of A times cosine of the angle divided by the norm of A. All I'm doing is I'm rewriting this as its equivalent form using the dot product. But the thing is, the norm of V and the norm of A is never negative. So the absolute value of a non-negative number will still be non-negative. So I can rewrite this as the norm of V times the norm of A times the absolute value of cosine. But what happens is the norm of A divides the norm of A. So I get a much cleaner, I would say another version, another way to represent the projection, the length of the projection of a vector along A. It's simply the norm of V multiplied by the cosine of the angle. And remember, this angle, this theta is between the vector V and A. So this is another way to find the norm. So we have the dot product with the norm, which is equivalent to taking the square root of the dot product. So we have a dot product version formulation for the norm of the projection of V onto A. And we also have if we're given the angle theta between the two vectors, I can just simply find a cosine of that angle and multiply it by the norm of V, and I figure out what the projection is. And the diagram behind that is the following. So if I were to have a vector V, and this is A, and I want to find the length, of this guy here. And I know the length of this guy. What's the length of V, of the vector V? It's the norm. Then applying the trig ratio of a right triangle, the horizontal component with respect to this angle theta here would be the norm of V cosine of the angle. So see, all these formulas that we've been going through, they may seem like strange or like we're doing something completely different, but it's just a reformulation of things that you already have done before, except that now we have this different notation and we have different geometric significance of what we're doing. Normally, when we deal with right triangles, we're not dealing with vectors, right? When the right triangles is just a static side, they're just static in space. But now with these vectors, this idea of vectors, you see how it just makes for more to talk about. Things are much more lively now, because now we have a sense of, we still have a sense of lines, but these lines now can be, or raised, I should say, pieces of lines that can be minimized, stretched. They could be inverted. So now there's more control, there's more manipulation of these objects rather than just having static sides. But again, those things that we learned with those static sides and geometry and solid geometry, in particular with trig, it's being applied once again. So I'm just saying, I hope that makes sense. I hope that that this formula is not just a formula because it works out so nicely with the algebra, but actually this makes sense because geometrically you can see how we get cosine theta. And again, we get cosine theta being absolute value because this angle theta could be either acute or it could be obtuse. And so we get the negative version. So see how everything stays consistent? Everything is consistent within this realm of mathematics. Everything is consistent. Great. Great, guys. Great. Okay. Any questions about this, guys? Any questions about orthogonal projections? The norm of orthogonal projections? None so far. Okay, no problem. So we've talked about orthogonal projections, orthogonal projections, orthogonal projections. So again, let's talk a bit more about these orthogonal projections. I'm gonna call this V, right? And then this is A, right? And then normally we project it in such a way that I'm given this new vector here. I'm gonna call this W, which is the projection, correct? It's the projection of V along A. And I'm gonna call this Z. So then I have a vector W and a vector Z. And this here, this V vector is also can be written as this V vector can be written as the sum of W plus Z. And we know that one, V is a sum of W plus Z. And we know that W times the dot product of Z is 0. So these are two things we know about orthogonal projections, right? So in other words, it's like saying, give me any vector, I can rewrite it as two vectors that are orthogonal and that add up to the vector that I'm given. Or you can think of, hey, I have a vector whose side is the hypotenuse of a right triangle. And W and Z represent those right triangles. So what do we know about right triangles? It obeys the Pythagorean theorem. And again, this is something we've discussed in the beginning. What is the Pythagorean theorem? How that relates to the distance and all that, right? So what do I know? I know that A squared plus B squared equals C squared. But what is my A squared here? What is my A squared? The norm of W. Very good. It's the norm of W. And then what would be my B squared? It would be the norm of Z. And what would be my C squared? It would be the norm of W plus Z. So what I just wrote for you is the Pythagorean theorem for vectors. If W is orthogonal to Z. So if we have two vectors, W and Z, then this holds. This is the Pythagorean theorem. And now I just want to say, how do you prove this to be true? What would be the little proof that we do for this theorem? Since it's a theorem, we can prove it. How do we know that this is true? This is true for Pythagorean theorem. Pythagorean theorem is something that we apply in the two-dimensional world and the three-dimensional world. How do we know this applies for any n-dimensional space? So I extended the Pythagorean theorem from the two-dimensional space, A squared plus B squared equals C squared. And now I'm extending this to n-dimensional space where W and Z are vectors in Rn. By induction, so this idea of induction continues again, right? But suppose W and Z are already they're already in Rn, and Rn is some arbitrary n-dimensional space. So suppose W and Z are in Rn, and W and Z are orthogonal. I'm going to write it as WZ are orthogonal. Remember how we do this again? We have this equation that we want to prove to be true. We want to show that it's true. And so the idea is show that the left-hand side equals the right-hand side. So what is the left-hand side? The norm of W squared plus the norm of Z squared equals, what does this equal? What does the norm of W squared equal? What's another way to rewrite this? W dot W, that's right. So we got W dot W plus Z dot Z. That's the left-hand side, right? This is the left-hand side. Now, does the right-hand side equal the same thing? What does the right-hand side equal? We got the norm of W plus Z squared. According to what we just said, the norm of W plus Z squared should equal what? W plus Z dot product with W plus Z. So what is this going to equal? Well, dot product is distributive over multiplication, over addition. So we can apply the foiling method. And I get that W dot W plus 2W times dot product Z plus Z dot Z. That's when you FOIL everything out. And remember, the dot product is commutative. So I can rearrange W dot Z with Z dot W. But what do we just show? Are these the same? I show that the left-hand side equals this. I show that the right-hand side equals this. That's right, Mir. They are the same. Why? Because this dot product here equals 0. Why does it equal 0? Because W and Z are orthogonal. So to really write this in a more, like, you can, sometimes what happens with proofs is that we do like some scratch work. This is like our scratch work. So in a way, it's like, how to describe this? This is like walking through a path of snow and you leave your footprints, but as you move, right, you cover those tracks. So that's what I'm doing here. I'm moving through the proof, trying to see how I should approach it. And I'm like, okay, I see that the left-hand side does equal the right-hand side, but now I want to smooth this out because this isn't that smooth, as you can see. Like it's a bit clunky because I started with the left-hand side. And as you can tell, the left-hand side, it kind of seems, if you just look at the left-hand side, how do you get from the left-hand side to the right-hand side? It seems kind of, it doesn't seem to flow so nicely. So actually the more clean, the cleaner way is to start with the right-hand side first. Why is that? Because it's a little smoother to get to the left-hand side. It's just about style. This stuff here is just about the style behind it. So W plus Z, the norm squared is W plus Z times W plus Z, dot product, right? And so I get W plus 2W times Z plus Z times Z. But this equals W dot W plus Z dot Z, which is the norm of W squared plus the norm of Z squared, which equals the left-hand side, which is the end of the proof. And you can say that this equals 0 because they're orthogonal to one another. So it looks like we just rewrote the proof, but it's just the flow of it is a bit cleaner because I go from the right-hand side to the left-hand side. Mir, yes, you have a question?
Yeah, so we didn't actually need the top left-hand side part, right? We could have just done the right hand, the bottom, the last thing we did, right?
Right. So that's exactly what I mean by it's like you're walking along a path of snow and you're just covering up your what you left. And so you're like, oh, I didn't have to do all of that, but I'm at this particular point. It's like I didn't have to do all of this. I could have just started with this. But sometimes you have to go through this to understand how to start. Because what did we start with? We started with left-hand side just blindly. We started with the left-hand side. But if you can tell, the left-hand side, to get to the right-hand side, just from here, you would have to have had the foreknowledge that there's a 2WZ that pops out of somewhere so that I get to this point here. You would have to have that foreknowledge. So you would have to already understand, oh, I'm adding by 0, and this 0 is embedded in the W dot Z. That's not as clear if you start from the left-hand side. If you start from the right-hand side and then you're like, oh yeah, this goes away because they're orthogonal, and henceforth, oh look, I got what's on the left-hand side, then it flows a little bit nicer, doesn't it? So all I'm saying is that sometimes this is necessary. Sometimes this trying to understand how to start has to occur. Proofs are nice end products, but usually the way we think is not the way the proof is outlined and written out. That's why sometimes reading proofs are difficult because the insights that sometimes the proofs have are hidden. And so that's why it takes a bit of time for the reader to see, hey, what did you do? How did you know that worked? Like sometimes that happens. and sometimes trying to create your own proof, it takes some time to work things out. Sometimes you have to like experiment and see, is there a pattern to this? But again, that's another the whole idea of writing proofs is an art. It's not a, I know if you guys took discrete math, there seems to be just a category for different techniques of proving. So you have induction, you have strong induction, you have contradiction, you have by exhaustion, you have these different methods of proofs. But it actually is an art. It's not always that cookie cutter. It's not always that clear as to how to approach a proof. And it's very interesting, particularly in linear algebra. You see a lot of proofs in linear algebra. But okay, so we proved that a Pythagorean theorem, the Pythagorean theorem version of vectors is embedded in this formula there. Okay, great. There's one thing I wanted to talk about that we missed a bit. So I want to talk about cross products, but before that, I want to talk about a way. You know what? Let me talk about cross products first, and then segue into what's called Cramer's rule. So for those of you who took physics, for those of you who took multivariable calculus, we talked about the cross product a lot, right? So what is the cross product? So we have two vectors. So let V and W, and this cross product idea is particularly in three-dimensional, is applicable to R3 only. So let V and W be vectors in R3. So we write the cross product V dot W. So the cross product of V and W is given by, does anybody remember what this equal or what this represented? It's an orthogonal, not component, but it's an orthogonal vector we get at the end, right? We get a vector that's orthogonal to both V and W. And so this idea of cross products is what's utilized to find the equation of a plane, because with two vectors, you can find the plane that those two vectors span. So if once you find that plane that those two vectors span, if you apply the dot product, I mean the cross product, not the dot product, you get that vector that's orthogonal to both of those vectors. And once you have the orthogonal vector to that plane, you can find the equation to that plane and so on. But what's the formula for that? V dot W is determinant of V times W. There is the determinant. There's definitely the determinant. But it's given by this. It's given by I hat, remember I hat, J hat, K hat. And then we have V1, V2, V3, and W1, W2, W3. Remember the absolute, the lines, the vertical lines are indicate determinant. So it's determinant of this matrix where the first row are the symbols for the standard basis vectors, which is I, J, K. We talked about I, J, K being E1. It's the same thing as saying E1, E2, E3, right? And then the second row consists of the vectors of V, which is the first vector here. And the third row is the vectors of the second vector W that we have here. So if we are to evaluate this vector, I mean this determinant, what we're going to do is we're going to apply row expansion, cofactor expansion, along row 1. So how do we apply the cofactor expansion? Does anybody remember? Remember, do you guys remember the determinants? So remember, this would be like our A11, A12, A13. So if I apply the cofactor expansion, exactly, Mir, you strike through the row 1 and row 2, column 1, row 1, and then you find the determinant of that smaller submatrix, and that is associated with the entry I. So this would look like A11 times C11 plus A12 times C12 plus A13 times C13. What is A11? That's I. What's C11? That's the cross product of V2, V3, W2, W3. And then plus, what is A12? A12 is J. Now this is times the C12, right? This is the cofactor C12. And remember, the cofactor C12 is -1 to the 1 plus 2 times the minor of 1, 2. The minor is the submatrix, determinant of the submatrix. When we cancel out, strike through row 1 and strike through row 2. And so what are we left with? We get V1, V3, W1, W3. But this now becomes a minus. This is J hat. And then plus K hat. Strike through the first row, third column, and I'm left with the submatrix of V1, V2, W1, W2. And if you apply the determinant to the 2 by 2 matrix, what do we get? We get V2, W3 minus W2, V3. This is what will be multiplied by I minus this becomes minus V1W3 minus V3W1, this is J, plus V1W2 minus W1V2, that's K. So what we just found was that U cross product this with W, this equals the vector V2 W3 minus W2 V3, comma, I'm gonna distribute the negative, so this becomes V3 W1 minus V1 W3, comma, V1 W2 minus W1 V2. Does that make sense? Do you guys remember this? And there's something embedded with this, right? Called the right-hand rule. So you have to use your right hand for this. And so the order of the cross product matters. If I take V and cross product it with W, right? You can think of V being, if you extend your fingers this way, if you see the screen, right? And if you do this yourself, then V would be the index finger pointing this way. W would be the middle finger pointing in the orthogonal, in a orthogonal fashion to the index finger. And so the idea is that when you put these fingers in this fashion, where the pointer finger is pointing forward, the middle finger is pointing to your left, and the thumb is pointing upwards, you have the rule for cross product. So this would be U, this would be this would be V, this would be W, and this here would be the cross product. This would be the result. This would be U cross W. If you do it the other way, where you say, if this is V, and instead of saying this is first, then you say W is first, right? Then you would have something like this. I don't even know how to like do this. But you would twist it in a way where the cross product will be switched. If that order is switched, then the result will not be the vector pointing upward, it will be pointing downward instead. And you can also visualize that or see that when you switch the sign of this. Remember when you switch the rows of a determinant, you switch the sign of the result. That's exactly what happens. So you would switch the sign of this. If you were to call this W and call this V, you would switch all of this around, just put a negative. And that's why you would have an inverted version of the result. Does that make sense? So see, all of this is consistent with the rules of determinants. Switching it one row, swapping it, negates the determinant, which results in a different the opposite vector. Okay. Okay. So beyond being able to apply this formula to vectors, let's do one. Let's do an example of that. So let's say I have, let's suppose I have a vector v equal 1, 2, -2, and w, which is 3, 0, 1. And I want to find the cross product. So I can apply the formula, which utilizes the determinant of this matrix. And I know this would be 2, -2, 0, 1. This would be minus 1, 3, -2, 1, j, plus 1, 2, 3, 0, k. The determinant of this would be 2. The determinant of this would be 1 plus 6, which is -7. And the determinant of this would be -6. So this here would be the vector. This would be the vector 2, comma, -7, comma, -6. Right? So this would be my cross product. This would be the vector. So v dot w, the vector v cross w, pardon me, is orthogonal to both v and w. It's orthogonal to both. Now, what I'm also going to be interested in, obviously, is the norm of the cross product. It has interesting properties, this norm of the cross product. So what is the norm of the cross product? Well, you can think of this as finding the straight up just the norm of this, right? This norm of this would be the square root of this times this times this. So I'm interested in the norm of u, pardon me, of v cross w. I want to know what this equals, or how can I interpret this? But there's some relation with sine theta. And the idea is the following. If we have u and v, this is u and this is v. And you can think of this as the parallelogram rule, right? This is v again. This is u. Pardon me, I'm using v and w. This is v, this is w. And there's something that we haven't discussed as of now, but it's something called the Lagrange identity. You can verify this on your own. that says that the cross product of u of v and w squared equals the norm of v of v squared times the norm of w squared minus the dot product of v dot w squared. And you can arrive at this conclusion if you were to individually find what this is, right? Which is v1 squared plus v2 squared plus v3 squared, and then multiply that by w1 squared plus w2 squared plus w3 squared, and minus the v1 times w1 plus v2 times w2 plus v3 times w3. If you square this, if you subtract this expression here, you would get exactly what v cross w squared is. And v cross w is this. If you take the norm of this, which is to take this and square it, this and square it, this and square it, and take the square root of that, well, if you square that, you get rid of that square root. So if you take this and square it and you add it to this squared and you add it to this squared, you would get this stuff on the right. And of course, I'm not going to go through the tediousness of what I just said that you can do, but you can check it yourself if so be it. But this is called like Lagrange's identity. And then what happens? Well, because this is the case, look what we get on this section here. What is v dot w again? V dot w is the norm of v times the norm of w times cosine theta squared. This is squared. And this equals the norm of v times the norm of w squared minus the norm of v squared times the norm of w squared times cosine squared theta. Right? But then what do we notice? I have the norm of v squared w squared minus the norm of v squared w squared, but then I have this cosine squared attached to the second expression. That's okay, because I can factor out this norm v squared times the norm of w squared, multiply that by 1 minus cosine squared theta. But if you guys remember the identity for the trig identities that exist, 1 minus cosine squared can also be rewritten as what? Does anybody remember?
Sine squared.
Good. It is sine squared theta. So what did we just find? We found that if I take v cross w, the norm of that squared equals the norm of v squared times the norm of w squared times sine squared theta. Take the square root on both sides, and I'm left with the norm of v cross w is equal to the norm of v times the norm of w times the norm of sine squared, which would be absolute value of sine. And we said all of that, all of this, not just to show you that the norm of v cross w is the norm of v times the norm of w times sine. Go back to that little diagram that I drew, right? First of all, what kind of shape is this? It's a parallelogram. This side length is what? not V, but norm of V. That's the side length. And then what's the side length here? Norm of W. Right? And then what's the angle between them? Theta. And then if I draw this line here, what is this orthogonal line segment that I drew here? That is called the what? The height, right? And the height can also be written as what? Using theta. It's the hypotenuse times sine of theta. The hypotenuse is what? The norm of V multiplied by sine theta. So then what am I really describing here? I'm not just saying that this is the formula. Hey, look, it's the formula. What also is the norm, the length of the norm of the cross product V and W? What is that also significant of, geometrically speaking? Does anybody see that? Does anybody see it yet? No? What is the area of a parallelogram? Anyone? It is equal to what? Length times width. Yeah, and usually we write the word base times height. It's the base of the parallelogram, which would be here, times the height of the parallelogram. Base is here times the height is here. So the norm of the length, which is the length of the cross product of V and W, that length of that vector that we find that's orthogonal, the length of that vector is exactly the area of the parallelogram spanned by the both vectors V and W. That's the punchline. So the length of the vector, which is the cross product of V and W, represents the area of the parallelogram spanned by the vectors V and W. So that's a geometric representation of the length of the norm.